there became lots of evidence to show there's a tremendous amount of very stringent, strict ordering that goes on inside the nucleus.
We're used to looking at diagrams where the nucleus is shown as a little ball with a plus sign in it, and the electrons travel in rings which are well-defined orbits. The nucleus is the same way. The protons and the neutrons can be treated as forming structures. You can think of it as rings.
And so, in fact, there are these configurations where the protons can line up in a special way, in these sort of ring structures, that will give a greater degree of stability to the nucleus as a whole than if they're in some other random or messed up order. And same thing happens with the neutrons.
Just like the electrons that orbit the nucleus, the stability of the nucleus depends on how full these rings are. When you have just the right number of protons,
That is a configuration which we consider magic.
and just the right number of neutrons as well, that's called doubly magic.
So what's so magic about that? These magical numbers of protons or neutrons are such that you have the maximum stability.
That is a very strong nuclear configuration.
Theory predicts that element 114 should have this kind of doubly magic nucleus. So it should be, despite its tremendous size, incredibly stable. Seaborg would have to change his approach.
Don't add one particle at a time, add 20 particles at a time, add 40. And so that's like slingshotting over that sea instead of trying to march across it step by step.
And Glenn saw this as a giant leap across a sea of instability of things that you couldn't make to an island sticking up out here.
An island of stability.
So that was what was motivating Seaborg. Could you jump this inhospitable sea to get this, what he hoped would be a magic island, an island of stability? Way up here, where you have all the way up to 114 protons and 184 neutrons. That was the next spot that he thought where you have this sort of magic stability, both a filled ring of protons and, crucially, a filled ring of neutrons.
Where these huge atoms might last long enough to hold in your hand, to look at. Something new in the universe.
How badly did he want to get to the island of stability?
He wanted it bad. He really did.
And tried for 30 years?
Yes, basically yes. We all thought that if he could discover super heavy elements, we could get him a second Nobel Prize.
So how we can realize this dream and leap to element 114? Well, plutonium has 94 protons. Calcium has 20 protons. Add them together and voila, 114. But how exactly do you add atoms together?
You have to accelerate them at one another very, very fast. So
Throwing them at each other.
Throwing them at each other. You can almost think of it as bowling. Each calcium ion is a bowling ball. And as the calcium approaches the target, it sees a set of plutonium pins. And there are an awful lot of other balls. The calcium just misses the pins completely. We will put somewhere between 10 to the 18th and 10 to the 19 balls through a target. 10 billion. There is that one sweet spot that if the calcium hits the thing, you get the element 114 strike. The calcium and the plutonium fuse, and you have an element 114 that survives.
Did they make it to the island of stability? Almost, but not quite. In 1998, Moody's team, in cooperation with Russian scientists, was able to bowl the magic number of 114 protons, but fell short of the 184 neutrons needed to achieve that double magic. In other words, while they still hadn't landed on the island of stability, they were this close, just at its shores, and that was no small feat.
I said to myself, I have to call Professor Seaborg and I have to talk to him. One of the great disappointments in my life was we couldn't have done that experiment 2 months earlier. He never knew about the result. He had had his stroke. He passed away a few weeks later.
Never knowing his magical island had been sighted. With Seaborg gone, Moody now continues the hunt for element 114's missing neutrons.
There were 10 neutrons short, but where the maximum effect should be.
And those neutrons mean everything.
Big difference. The difference between existing and non-existing.
Those neutrons may hold the answer to how long it might last.
Whether we're dealing with something that's very long-lived, like on the order of the age of the universe, or whether we're dealing with something that's minutes or hours.
But even minutes or hours is long enough to see, touch, and study.
And a chemist's eyes light up because you can start thinking about doing all the chemistry experiments in the world.
Experiments to reveal what its properties might be. Perhaps a material with uses we haven't even dreamed of.
Maybe a ball of gas, actually. There are some predictions that it's actually a gas.
Well, it could be a really heavy metal.
The periodic table says it should be a heavy cousin to lead and tin.
So that would be very exciting because then we can prove that periodicity is, the chemical properties continue to extrapolate as you expect from the periodic table.
We would learn a tremendous amount of just basic nuclear physics. There's still these questions that we just can't figure out until we can make the stuff, study it, and ask these questions in the laboratory.
One thing is certain, we will have something the stars did not leave behind. If only we can get to that magic island.
We think it's there. Can we get there? Can we plant our flag in the sand?
Maybe Ken Moody can.
That's the mystery of the island of Steele Lake.
Okay. So I like that. It gives you, gives you a little bit more about the nucleus, kind of your introduction to nuclear physics. All right. So the interesting thing, so they've named 114. They're working on elements past that. It did uphold